the ratio of these different sugar. We do the same for the matched patient, okay, the same chain, the same sugar chain, no sialic acid, 1 molecule of sialic acid, 2 molecules of sialic acid. So what we see, for example, in one pair, control versus patient, we can see here a ratio of 1 to 3 to 3. The patient has 1 to 1 to half. So here we can see clearly there is hypocyanidation of this sugar chain. Then we look at the same sugar chains in another pair of patient control, okay, 19 and 19, and here we see a ratio of 1:1.2 and 1:1.5. So here we don't see any hypocyanidation at all in this patient. Okay? So we did that for all our patients, for all the different sugar chains, and for example here you see other sugar chains like B1, 1 molecule of sialic acid, B2, 2 molecules of sialic acid, or C1, C2, C3. Okay? So we did that for all, systematically for all the chains that had sialic acid on them, and we did the same for the lipid sugar chains, AA1, A2, BB1, BB2, etc., etc. And in fact, we can see a very big difference between the different patients and controls. Some are hypocyanulated, some are hypercyanulated, some have no change. So our conclusion is, here for another example of the lipids. Anyway, our conclusion is that there is no consistent difference. There is sometimes some difference in some chain, but there is no consistent difference that we can say that's the chain that is hypocyanulated and probably leads to the disease. Okay. So at this point, the question is that the enzymatic activity is reduced to about 30%, but there is no consistent change in overall circulation, and again no consistent difference in individual sugar chains circulation profile. So the other option that we can think of is that GNE, in addition to its role as a key enzyme in the synthesis of sialic acid, is involved in some other unrecognized functions that could contribute even more than the sialic acid to the pathophysiology of the disease. Okay, so we undertook this project with many different approaches. Okay, you can see that on the list. And I will not talk about all of them. I will just summarize different points and talk about more detail to the GNE partners search. Okay? So from all the other studies, we could learn some things in GNE biology. We think that GNE may have a role in signal transduction mechanism that could be related to apoptosis, to cell survival, and probably do that through mitochondrial pathways. And I think that Dr. Arya will talk about some aspects of this in her talk, of her studies on that. Also, by proteomic signature of GNE myopathy cells, we can see that most of the genes involved differentially expressed, proteins differentially expressed, respond to biogenesis and remodeling of the sarcomere organization, and that GNE is essential not only to brain development as we knew before, but also to skeletal muscle development. So now I want to talk about the GNE protein partners study. we think that if we can find proteins that interact with GNE, we could learn about their function and then assume that GNE is one of these pathways, of these proteins involved in the pathways that we can find. So this work has been done mostly by Shiram Sili and Abi Razi. And what we have learned from our first studies on that is, first of all, that GNE is expressed at the Z line of the sarcomere and also at the M line. Okay, that's one thing that we can see. The second thing that you can see, that alpha-actinin 1 is expressed in muscle. Indeed, alpha-actinins have 4 known isoforms, 1 to 4, and the muscle isoforms known are 2 and 3, that are in fact the markers for the ZBs. Okay? And the non-muscle, the ones that were known as non-muscle forms, 1 and 4, are 1 and 4. But here we can see that alpha-actinin 1, in fact, is expressed in muscle, okay, is expressed at the muscle, and it is not overlap or not totally overlap with actinin 2, okay. So in fact, it is at both sides of the Z line, okay. So we have here another information. And the third thing that we are learning is that GNE binds to alpha-actinin 1 and alpha-actinin 2. So when we look for GNE protein patterns by traditional methods, in fact, we couldn't really find any candidate protein till we get to use the SPR technology, affinity measurement with biomolecular interaction analysis. This is a technology that is based on optics. Okay, when you have a protein that or a molecule that is bind to a chip, covalently bind to a chip, and there is a polarized light that hits it, this light gets reflected at a certain angle. If the mass of this molecule changes, the angle of the reflection light will change, and we can measure that by a curve. Okay? So what we did is to bind to the chip, immobilize the protein GNE, and pass as a second protein a muscle extract, okay, to see if we could change the reflection of the angle of the reflection, meaning that something has bind to GNE. And by this technology, we could find that GNE binds to alpha-actinin 1 and to alpha-actinin 2. Then what you can do with that technology is to measure the kinetics of this interaction. And here, for example, for actinin 2, we see by increasing the amount of alpha-actinin 2 that the affinity of wild-type GNE to actinin 2 is about 9. Okay. On the other, excuse me, not the affinity, the constant parameter. When we do that for actinin 1, we saw that this constant was 68. Okay, meaning that the affinity of actinin 1 to GNE is much lower. It's the inverse. Okay, it's much lower than the affinity of actinin 2. So GNE binds to actinin 2 in a much stronger mode. Okay. Now, if we look at the mutation, the N743 T mutation, we can see for actinin 2 that we don't have any real difference in the affinity between the wild-type protein and the mutated protein. Okay? And the same with actinin 1. So the wild-type and the mutated protein do not bind differently to actinin 1 or to actinin 2 in this assay. Now I remind you that in this assay, GNE is immobilized into the chip, and in fact we don't know where is the binding region of this protein. So these are not really physiological conditions that can allow us to really study the interactions of two molecules. So to better understand that, we have turned to another technology called microscale thermophoresis. In this technology, you can use the molecules in a more native conditions because they are both in suspension, in solution. Okay? So this technology is more sensitive, and you have to label, fluorescently label one of the proteins. Okay? So how it works, very rapidly, you put your molecules in a capillary, okay? And at the initial state, the molecules stay in a certain position when you can measure fluorescence, because this protein now is labeled, so you can measure this fluorescence, and then you hit the capillary, and by hitting the capillary, the molecules will begin to move away from the source of heat. Okay? So the fluorescence will be coming down because you have less molecules at this certain point. Okay? So now, if the mass of the molecules is bigger, the movement will be slower. Okay? So the decrease in fluorescence will be less detected, okay? Because the molecules will move much more slowly. Then you can measure the difference of decrease and in fact quantify the kinetics of this reaction and calculate the affinity of this interaction. So by doing so, what we did is to compare the binding affinity of actinin 1 to GNE versus actinin 2 to GNE, and to GNE wild type versus the mutated GNE. And what we found is that when we use actinin 1, again, we don't see a real difference in the affinity between wild type GNE and the mutated GNE. Okay, this is something like half, but it's not enough for this kind of assay. And when we use alpha actinin 2, in fact, we see a dramatic change